Well, good evening and welcome to Copernic FNL Friday Night Livestream. Great to have you with us this evening. And for those of you who may not know me, I'm Drew Desker. I'm the director here at Copernic, and really looking forward to this presentation this evening, and but also just looking forward to presentations that we are going to be doing over the next few weeks and into the next few months. Just to let you know, some upcoming live streams we're doing. Next Friday night, January 22nd, is a talk on astro imaging with smartphones. These things are really quite something. And so Jeremy Carty, our live stream astronomer, is actually sort of got his start doing astro imaging with his cell phone, and so he'll talk about how he sort of got into that and some techniques to make it a rewarding experience for you. Following Friday, January 29th, is Phil Cooper, who is just an extraordinary wealth of knowledge on the original space program that NASA had, and his program on the 29th will be America's Forgotten Space Program, in the Gemini program. So that was actually very important because it really helped lead us up to a point where we could finally get astronauts on the moon. Following Friday, February 5th, we're doing a preview of the Mars 2020 Perseverance rover landing. Tish Brizzi of our staff here is a NASA JPL Solar System Ambassador, and she's going to give you an overview of what Perseverance is about. We did the live stream of its launch. Now we're going to sort of catch you up on what we expect Perseverance to be able to do for us. And so that'll be on February 5th. February 12th, Robert Burns from the Copernic Astronomical Society will do Winter Skies. Again, winter is often one of the best times to go looking into the night sky, albeit you just got to dress warmly enough. But so he'll tell you about what you can expect to see in the winter skies. And then finally, on February 18th, which is a Thursday afternoon, is the actual anticipated landing of the Perseverance Mars 2020 rover. And we will cover that live with some color commentary in the chat. And then finally, the next Friday is February 19th, which is actually Copernic's birthday, and which is what the Copernic Observatory is named after. And we will have our winter star party. We're still finalizing the speakers for that, but so keep tuned. Anyway, now we are going to move on to our actual program. Alessondra Springmann is finishing her PhD down in University of Arizona, and has spent a couple of years at Arecibo. And so when I was looking for somebody to talk, they said, all right, Alessandra's the person you want to talk to. And so we look very much forward to hearing about her work down there and what the whole Arecibo instrument was all about. And now that it's not currently operational, possibly think about what we, how can we move forward from here. So, Alessandra, we're going to turn it over to you. All right.
Okay. Let's make sure I can. Okay. Can people see this?
Yep, you're good.
Okay. Great. All right. My name's Alessandra. I'm going to be talking a bit about the scientific and a little bit about the cultural legacies of Arecibo Observatory tonight. And this is going to be an asteroid-focused talk because I study asteroids and comets. And I can talk a little bit about the astronomy as well as the aeronomy and ionosphere studies, but I'm an asteroid person at the end of the day. So I hope you enjoy, and please ask lots of questions in the chat. Right. When we think of asteroids, often we think of The Empire Strikes Back from 1980. We think of the Millennium Falcon navigating the asteroid field. But Actually, asteroids, I think, are a lot more interesting than just random chunks of styrofoam that were painted and hung in some sound stage run by Lucasfilm. So asteroids turns out there's a lot of them. There's over 1 million asteroids that we know about, and there's about 10,000 asteroids that come close to Earth. So where do asteroids come from? By the time I'm done with this talk, hopefully you will have a better sense of what an asteroid is, where it comes from, where it is, and why we care about asteroids, and also how Arecibo Observatory observed them. So asteroids come from the protoplanetary disk that our solar system formed out of. So about 4.6 billion years ago, our solar system started forming. Gas and dust condensed into pebbles and then boulders and planetesimals, and some of that even made it into planets and asteroids. Some of that became the little planet that couldn't and formed into asteroids in the asteroid belt, which are smallish planets, and some of that material falls to Earth as meteorites. So meteorites provide samples of the origin of our solar system and extraterrestrial bodies in general. These white bits in this meteorite is a Yende, which fell in Mexico in the late 1960s, just as the Apollo program was ramping up and all these laboratories are getting ready to study extraterrestrial materials. So before even the Apollo astronauts went to the moon, suddenly we had a source of extraterrestrial materials. So the white flecks in this meteorite are about less than a centimeter in size. They're just a couple millimeters across. And they're the first things to condense out of our solar nebula as our solar system was forming. So asteroids and meteorites are ways to study things that are billions of years old, the building blocks of our planets. And so meteorites are one of two ways that asteroids come by Earth. So we have meteorites, and then we also get flybys of asteroids as well. So sometimes when we think of asteroid flybys, we think of going back to our Atari console, flying around, shooting asteroids. And that's, again, unlike The Empire Strikes Back, this is really not anything resembling reality. So let's get oriented to where the asteroids are. Asteroids tend to hang out in orbits between Mars and Jupiter. There are about 1 million asteroids in that area. If you took an asteroid and scaled it down to the size of a potato, the asteroids would be miles away from each other. So there's a lot of asteroids, and as this animation shows, there's a lot of asteroids, and when we look at these animations of the solar system, we see all these green dots, which are the main belt asteroids. Again, there's over 1 million main belt asteroids. We think they're really close together. And so the red asteroids are the near-Earth asteroids, which are the ones that come close to Earth. And there's about 20,000 of these near-Earth asteroids that we think of. So again, we think of asteroids as being super dense, being really close to each other, and we think of C-3PO freaking out, telling Han Solo that the odds of successfully navigating an asteroid field are 3,720 to 1. But every time we've sent a spacecraft through our asteroid belt on Earth, the spacecraft has survived. So at least in this galaxy, the odds of successfully navigating an asteroid field are actually 1 to 1. So we've got lots of asteroids. They tend to hang out between Mars and Jupiter. There's a few that come close to Earth, and they're really far apart. So one of the reasons that we study asteroids is to prevent broader impacts on Earth. This is Behringer Meteor Crater in northern Arizona. Some of you have maybe visited here. It's right off I-40 east of Flagstaff. It's a mile wide, and it formed in about 10 seconds. It happened really quickly, and it was probably a very rough day for a lot of life in northern Arizona when this happened. So we see these impact craters on Earth. We see them, like Hudson Bay there's a very large crater in Hudson Bay, but it's mostly filled with water, so it's hard to study. And a lot of other ones are disguised or eroded away. But sometimes we see meteorites come visit in a slightly more spectacular fashion. In February 2013, in Chelyabinsk, Russia, we learned a startling fact. Every Russian has a dash cam, and pretty much every Russian with a dash cam in this town captured a video of this asteroid exploding in the atmosphere above Chelyabinsk, Russia. And We also learned that everyone will go outside to look at the asteroid coming through the atmosphere, and then will be very shocked when the shockwave hits them and breaks lots of glass. So we study asteroids because we want to learn about our solar system and how it originated. And we also study asteroids because it's important to figure out, to find them before they find us, and find ways to tell them to get lost, go away if they do come by Earth. In order to do that, we need to figure out, where is the asteroid? What's its orbit like? How big is it? What is it made out of? Is it dense? Is it fluffy? Is it made out of metal, or is it made out of rock? And then finally, another reason to study asteroids is for space resources. When you have one asteroid mining company, they're a little weird. When you have two asteroid mining companies, maybe it's a respectable industry. And so a lot of these asteroid mining companies may have been a little bit ahead of their time, but the general idea is that if you don't have to bring water for drinking, shielding, or rocket fuel into space, and you can get all that from asteroids, you can have a more sustained human and robotic presence in space to do exploration or to develop space industries. So we have lots of compelling reasons for studying asteroids. What do they look like? So we've visited a few asteroids over the years. These are mostly asteroids that were photographed as part of missions to go visit other objects. This big one, 21 Lutetia, that's over 100 kilometers across, was visited by the European Rosetta spacecraft when it was going off to visit a comet. Ida and Dactyl were the first spacecraft visited by asteroids. It was visited by Galileo in 1993. So a lot of these asteroids aren't the stars of their own show. They're sort of, okay, we're sending $1 billion spacecraft to go do a thing somewhere else, but there's a convenient asteroid on the way, so we'll turn on our cameras and make sure everything works. So that's usually how we see asteroids, and we can resolve them as these really interesting worlds. They've got craters, they've got some tectonic features. The comets that we see have, sometimes they're one lump, or maybe they are shaped more like a bowling pin or a termite. Some of them look like potatoes, some of them look like goldfish. So we're seeing this huge variety in asteroid shapes and sizes as spacecraft have gone by. But if you're trying to study hundreds of asteroids or even thousands of asteroids, you can't spend $1 billion every time you want to go study one, as great as that would be. So most asteroid studies are done from ground-based optical telescopes like the one you've got there, and we see asteroids as points of light. So there are about 2 or 3 asteroids in this movie, just flipping back and forth. And this is how asteroids are discovered. We take images some amount of time apart, and you see what moves between the image. And anything that moves is probably an asteroid or a satellite or probably an asteroid. So you can look at these asteroids as points of light, and this is how we know that there are millions of asteroids out there. But ground-based observing has its limitations, as I'm sure we are all intimately familiar. Arizona doesn't have this problem so much as New York and Pennsylvania, but clouds can often get in the way of observing. So this is a beautiful image taken of a gorgeous, typical Arizona sunset from Kitt Peak. And it's really hard to see asteroids or really anything through clouds at night. And also you can't really observe during the day. So there is a way to sort of bridge this gap between asteroids as points of light and fighting with clouds, and asteroids as these high-resolution HD images from very expensive spacecraft, and that is radar. If you are a radio person, maybe you've got a ham radio background, you know that radio waves aren't affected by rain, they're not affected by day-night cycles, they're not necessarily affected by clouds. And so this is where Arecibo Observatory comes in. It was this 305-meter dish in Puerto Rico. It's 1,000 feet. It was 1,000 feet across. Most stadiums would fit in comfortably with room to spare. And it was really unique among observatories because this is something that you can't do with an optical telescope, is that it had a radio transmitter on it. So if you do radar studies of asteroids, as well as more passive studies of galaxies and dust and gas further out in space, as well as ionosphere studies and also climate studies. It was actually built super quickly. It was designed by some folks at Cornell up the road in Ithaca. The original design was completed in 1960 and they finished it in 1963. The construction photos are always fun to look at. They built the towers first, and then they built the platform and raised the platform, and then they built the dish after that platform construction was finished. So why did they choose Puerto Rico? It was on US soil. It was a good latitude for looking at some atmospheric phenomenon they wanted to study. It wasn't too far north, and it wasn't too far south. It was away from a lot of radio interference. And there was this convenient sinkhole that was about 1,000 feet across, so they didn't have to do too much excavation. So this photo is dated from February 14th, 1963, which was just about 7 months before the facility opened. So construction happened really quickly back in those days, and it cost $10 million to build. So a lot of us are familiar with Arecibo Observatory from movies like GoldenEye, or for the younger crowd, people who played GoldenEye on their N64s. So there's a couple things that the Bond films did not get right. One is that the dish is not in Cuba, and while Puerto Rico is incredibly humid, the telescope is not underwater, and it does not come out from a lake. And so you can see a couple of aspects of the telescope that are really cool. You can see the platform, you can see the arm that moves, and you can see this big light antenna. The other movie that a lot of us think about when we think about Arecibo is Contact. And so Contact was filmed a couple of years after GoldenEye, and you can see the telescope now has this big Gregorian dome sticking on it, which was installed in an upgrade in the mid-90s to make the telescope more sensitive and also to improve radio astronomy and radar. So this is a map of, this is an image of Puerto Rico taken from the space shuttle, and Puerto Rico is about 100 miles across and 70 miles from north to south. And Arecibo, since my pointer is not working, is in sort of the upper left quadrant. You can see kind of a white spot just south from one of those big dust plumes that's going out from one of the rivers. And the telescope itself is a really beautiful structure. It's all triangles and this big circle, and there's really nothing quite like it that I've seen anywhere else. And so a couple things to note here. This image is taken a few feet above the center of the telescope, so about 400 feet up in the air. You can see the knees of some of my friends in the upper left. This big box that looks like an air conditioning duct is actually the waveguide for one of the radar systems for the ham radio folks. It's for the 430 megahertz waveguide. And you can see the hills of the jungle in the background, and you can see the control room. And this thing is really high up there. It's also really stable, which makes sense. If you want to do scientific observations from a platform like this, it can't move much. This is a photo that I took from under the dish. This is a perspective that you don't see often. So this is looking straight up at the dome, at the platform, at the circular track that the arm moves around. And if you're a Harry Potter fan, it kind of looks like the Deathly Hallows. This is under the dish as well. So the dish was perforated aluminum panels, which was important that you had light shine through because you wanted plants to grow under the dish so that you didn't get erosion happening. So these are a number of students, summer students from University of Puerto Rico who are getting the tour under the dish. And then for a sense of scale, this was an illustration done by one of our postdocs. This shows the size of the observatory compared to one of the asteroids that the observatory would look like. And so this is a 250-foot asteroid sitting in a 1,000-foot dish. And so this is not something that actually happened, but it shows you that you can, this observatory was routinely looking at asteroids smaller than the dish itself, which is not something most ground-based telescopes can say. You know, if you've got a 12-inch telescope in your backyard, you are not looking at asteroids that are 2 inches across. Ain't gonna happen. So how does radar work? Well, most of us who have gotten a speeding ticket or been pulled over for speeding at some point in our life kind of know that you have a source of the radio waves. The radio waves then reflect off whatever they're reflecting off, whether it's your vehicle or an asteroid in space, and they come back and they're collected by a radio receiver. And so radar is really good at measuring the velocities or how fast things are moving in space, which is great for getting information about how fast asteroids are orbiting in space. So in order to do this, you need a lot of power, which we'll go over, a big dish, which we've just talked about, and often a close target. So when asteroids pass close by Earth, perfect. So let's talk about how you get all this power to generate your radio waves. The Puerto Rican power grid, as many of us learned after Hurricane Maria, is not very robust. It was not very stable before that hurricane, and it was certainly less stable after. So in order to generate power for the radio transmitter, we had 4 diesel generators that would create 2 megawatts output. And so after the hurricane, it was very convenient that the observatory had these generators there and had the capacity to pretty much run its own power plant, because the observatory then was able to provide water, power to people in the surrounding community who didn't have those things. They wouldn't have access to those, to water or power for weeks or months. There are a series of high voltage transformers as part of the high voltage power supply for the radar transmitter. And this all looks, the circuitry is very simple at the end of the day. You have, a bridge rectifier, okay, some of us who've taken like laboratory electronics classes in college have built things like this. Except at Arecibo, what comes out of this is 2 million watts. You have 33 amps and 65,000 volts, and you get some watts. So the things that actually create these radio waves are called klystrons. This one is about 5 feet tall-ish. Klystrons are kind of like light bulbs, except for radio waves. They involve a lot of power and magnetic fields, and you get designer radio waves as a result. These things run hot, so they're cooled with about 300 gallons of water per minute. This is using tubing from a homebrew catalog from a company called Brewmaster to cool the klystrons, because it's not like you can just walk down to where Radio Shack used to be and say, hello, I would like 1 klystron. These systems are all sort of custom built and held together, sometimes with toothpicks and bubble gum. The control system for the radar was very vintage, definitely reflected the technology of the 90s when it was built. This was a bad night. There were a lot of things that had gone wrong. There was problems with the high voltage power supply oil, one of the pumps, the 480 volts AC component of one of the systems, and then the thing that says crowbar. If you're experienced with high voltage, in the bad old days of high voltage, if your power supply was going to overload, you would drop a physical iron crowbar off or the 2 terminals of your power supply to short it out. And so now there are crowbar circuits that would automatically trigger if the high voltage power supply was experiencing problems. So this is how that system was controlled. This is on the left. We have the world's most sensitive planetary radar receiver. Next to, on the right, the world's most powerful planetary radar transmitter. To give you a sense of scale, those apertures in the center are each about 5 inches across. And the reason there's this cover on a track on the receiver is because it's a really sensitive receiver. You don't want it fried when 1 million watts are marching out of the transmitter on the right. So when the system is transmitting, the receiver gets covered, and when it is receiving, that cover has to come off. These are some other of the radio astronomy instruments that were there as well. Part of the reason that dome was installed in the upgrade was that it makes it much easier to switch out receivers if you have the radio waves focusing to a point inside the dome instead of in that really long antenna. Everything is cooled with liquid helium to about 35 Kelvin. because radio works a lot better when your receivers are cold. And I said earlier that you have those diesel generators that generate 2 megawatts of power. Well, 1 megawatt got transmitted out of the klystrons, and 1 megawatt was dumped as waste heat. So that dome itself is 6 stories tall, and those fans will dump at were there to cool the transmitters. So the transmitters themselves are controlled with these very old school looking consoles. This is the console for the atmospheric radar, and if you've seen Contact, you'll recognize its tiled floor. And this is the cabling back-end system for the Planetary radar system. And so the telescope is a giant voltmeter. The signal isn't really amplified until it's finally converted into a power. So before you measure your signal, you can attenuate it, you can amplify it, you can filter it, and then you can finally send it into your computer. And the magic of radio is you can reprocess things many times after the data is collected and not lose signal. So this cabling was always fun. The first time my boss was showing me how to do it, I'm sort of sitting in the chair with this I was completely just, I don't know, stuck, just frozen. Like, how the heck have I learned how to do it? And within not too long, I was doing it pretty well. So this was the control room that we would use for radar runs. And because radar doesn't care about day or night or rain or shine, we would often, once a month, we would have these runs from about 8 or 9 p.m. till 4 or 5 in the morning. So you'd stumble out after sunrise. And our sleep schedules got a little wonky. And so sometimes, the office mate would find whatever opportunity he could to take a nap. So radar is really great. It's great because you can create your own radio waves, and because of that, you know when you're transmitting and what sort of radio wave you're transmitting and receiving. Because we know the speed of light, we can use that to measure the speeds of asteroids as well as the distances, and also get shapes and sizes of these asteroids, how fast they're rotating, do they have moons? We can transmit and receive all the time. Rain, clouds, lightning, and we got these higher resolution details of asteroids and comets than you could get with a ground-based optical telescope. Radar was also really great for orbit measurements, and you could take an asteroid that had just been discovered where there was some uncertainty in the orbit, and you could project its orbit out decades, if not centuries, and rule out future impacts with the Earth. So as we observe these asteroids, we see that the asteroid population is really diverse. And we see all these shapes of asteroids. Some of them are round, some of them are irregular, some of them are metallic dog bones, the size of New Jersey, like asteroid 216 Cleopatra. We see asteroids with moons, asteroids that rotate every few minutes, asteroids that take their sweet time and rotate once every couple days. And so I will take you on a little bit of a tour through the asteroid population. Let's see here. We'll skip this. If you care about radio astronomy, asteroid radar astronomy happens very quickly, much higher frequency resolution compared to radio astronomy. We're looking at a much narrower bandwidth. We know our radiation source because we made our own radiation. We made our own radio waves. And we have a fixed amount of total power. So I'm going to show you a bunch more images of asteroids taken from Arecibo, and as well as some companion telescopes. And they're not real images like you would see out the window of a spacecraft. What we're doing is we're taking a 3D object, like an asteroid, and we're trying to project it into a 2D image when we know the distance to points on the asteroid and how fast it's going. So this is really like not an image that you would see with your own eyes, but you can pretend that it is. So all these images, these little black and white things that look like sonograms, you can, for the most part, it's what the asteroid would look like. And it's kind of like trying to take understand what a potato is like by chopping it up into little bits and then trying to be like, okay, this is what the potato is like. So it works pretty well. You know, it's made of starch at the end of the day, and it still has a shape. All right, asteroid images. These are 3 asteroids. They're each about 400 meters across, and it shows you that there's this huge diversity in, again, shapes, even in these objects that are the same size. Another interesting thing that people have discovered since using Arecibo to study asteroids is that contact binaries, these asteroids that look like bowling pins or peanuts or termites, but they're about 14% of the population of asteroids over about 200 meters in size. And they tend to rotate really slowly. The other thing with these asteroids that we've been observing is that about 1 in 6 or 7 has a moon, which is kind of cool. And that these moons that are orbiting these asteroids all tend to have similar properties, that like our moon, they're tidally locked, and that they're showing the same face to the asteroid at all times. And they seem to be about a third the size of the parent body. This asteroid is one of those 400-meter objects that I showed you earlier. This was 2014 HQ-124, which is a terrible license plate name. This one got the nickname the Beast somehow from some, I think, one of these astronomy websites. It's like, it's not a beast, it's very pretty. But this was kind of a cool observation that we did at Arecibo, because for the first 2 images with the darker background in the top row, this was actually taken with a friendly, not-so-neighborhood telescope. So the folks at Goldstone in California, which is part of the Deep Space Network, they have a 70-meter telescope with a higher frequency transmitter than Arecibo has. So they transmitted continuously at this object, and Arecibo was able to receive. And so while Arecibo doesn't have that higher frequency transmitter, it has one of those receivers. So it was the transmit from one telescope, have the signal bounce off your asteroid, and receive it at another telescope. And so this works really well. However, Arecibo can't steer as much as Goldstone because it's fixed in the ground and can only point 20 degrees in either direction. So at some point, this asteroid moved out of the Arecibo sky, and so Goldstone had to transmit from their telescope and receive at another telescope there in California. And you can see that there's a lot less detail in those bottom 2 images. And the background is a lot noisier. And this is because Arecibo is 18 times larger than Goldstone, and so is 18 times more sensitive. So Arecibo was this really invaluable tool for studying asteroids, and had far more sensitivity than Goldstone did, and could therefore observe about 18 times more asteroids than the Deep Space Network telescopes. Arecibo also observed comets, including objects like this one. This was a comet that rolled by in 2014, and again, this was a time when we had to phone a friend. And one of those amplifiers and the receivers had warmed up, and so we couldn't use the receiver at Arecibo. Fortunately, the Green Bank telescope in West Virginia has a receiver on it that can receive signal from Arecibo. So we transmitted continuously to them, and they were able to receive. And so it was, again, one of those bistatic, transmit from here, receive over there. And this is about 10 meters per pixel. It's about 2 by 3 kilometers, and you can see these big scallops, kind of implying a lumpy surface on this comet. And it makes me think a lot about Comet 67P, Churyumov-Gerasimenko, which was the target of the Rosetta mission to that comet that arrived in 2000, that sent its little lander Philae in 2014. So another target of a space mission that Arecibo helped out with was Osiris-Rex, which is the Osiris-Rex Asteroid Sample Return mission. And let me see if I can get this acronym. Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. Whew. Regolith Explorer pretty much means let's go look at some dirt. It launched in September 2016. It arrived at the asteroid in 2018. It did its sampling a couple months ago, and the sampling went so well that they were actually overflowing with sample. The spacecraft has those 2 solar panels sticking out like wings. It's got a big high gain antenna, and then it's got that arm that sticks out, which is the touch and go sample return mechanism. And at the bottom of that, there's this doohickey that's about this big, which is this canister with a bunch of compressed gas. And because this asteroid is like 500 meters across, it's the size of the Empire State Building, it doesn't have a lot of gravity. So you can't go to this asteroid with like a pick and a shovel or a scoop and just scoop material off the surface, because pebbles and rocks and sand don't behave the same way in microgravity as they do on Earth with 1G. And so they actually had gas canisters in the sample head that would eject gas, and that would hopefully loft material from the surface of the asteroid, and it would get collected by the sample return head. And it actually worked out, and they did it so well that they were overflowing with sample. So a lot of talk when it comes to planning spacecraft missions is how do you reduce risk, right? You're spending $1 billion of the taxpayer money on a spacecraft to go somewhere. By golly, you want it to work, right? You don't want to have something fail spectacularly because someone forgot to, I don't know, convert from imperial to metric well, or anyway, probably too soon on that one. So this Arecibo Observatory was called to do a shape model of this asteroid. And it's part of why this asteroid Bennu was selected as a target for the Osiris-Rex space mission, was because there were existing Arecibo Observatory observations of this object. So Arecibo had about 10, 15 meter resolution on this object that was about 500 meters or so in size. So a little bigger than Arecibo, 2/3 larger than Arecibo. And they made a preliminary shape model for the spacecraft from this radar data. And a lot of people were skeptical early on of the shape model of this asteroid. People said it's got this ridge, that has to be an artifact of radar, that can't be right. And it seems to have like this bump in the North Pole and this bump in the South Pole. That has to be an artifact of the radar. There were a lot of skeptics and a lot of haters. And guess what? The spacecraft rolled up in 2018 and got images of the asteroid, and it looks very close to the shape model. The shape model was off by about 5%. And indeed, there was a bump in the south and a bump in the north, right, in about the same position. So radar is this incredibly invaluable tool for mission preparation and for mission planning. So this was, it's really nice to have your scientific results validated by a spacecraft rolling up and saying, yeah, this works. And this was a cool result from a little bit ago, that this asteroid didn't seem to get the memo that it's an asteroid, and it decided to start working like a comet, and that there was all these kind of plumes of pebbles coming off of this asteroid, that it was ejecting pebbles. So while you can try to reduce risk as much as possible with a space mission, you're still going to be surprised when you get there. Which is the goal, right? If you go to your object and everything, all of your questions have the answers you expect, maybe you shouldn't have been planning that mission. So in conclusion, radar astronomy is great. It helps us study asteroids as these sources of an accessible source of extraterrestrial material. We're able to start understanding this asteroid population, asteroids as a population. We've observed 500-ish asteroids with radar over the years, and it allows us to get their shapes and sizes and their orbits. And it shows us how diverse the near-Earth object population is. We see the round ones, we see the lumpy ones, we see the ones with moons, we see the ones that look like tops, the ones that look like termites. And it really enhances our ability to explore asteroids with spacecraft. So I also promised a little bit about the cultural legacy of Arecibo. And so, we've shown sort of the Hollywood version, but this is, we also, I think it's really important to talk about the human aspect of Arecibo. This photo was taken after Hurricane Maria in 2017. And a lot of people were asking me, Sandy, why do you care so much about the observatory after the hurricane? Shouldn't you be worrying about, the people who live there? It's like, well, you can't have an observatory without the people. All of these people live relatively nearby. They all have families. Some of them, there's multi-generational families who've been working at the observatory, since it was built in the 60s. Almost everyone has a cousin, an uncle, an aunt, a grandparent who helped build the observatory, or who worked at the visitor center, or who works in electronics, or as a telescope operator, or even as a scientist at the observatory. But the observatory is an integral part of the community, and it would not exist if it wasn't for the people around it. And on a basic level, after the hurricane, you have diesel generators, you have a source of power, you have a 600-foot deep well, so you're able to get a reliable source of water when municipal water was off or unreliable for months after the hurricane. There's a helicopter landing pad at the observatory, so FEMA was using it as a base for distributing aid to these surrounding communities in this mountainous, difficult to access interior. So it's, you can't have an observatory without the people, and the people around the observatory, it's beneficial to them to have an observatory nearby. One of the first things people will do in Arecibo after a hurricane is they'll clear the road to the observatory because they know it will help them out in the immediate days and weeks to have the observatory accessible. And one of the first ways we got any news out of Arecibo was Angel Vasquez, who's the telescope director and a huge ham radio nerd. He drove and then walked the last few miles to the observatory to check in and to see how everyone was. And so when the telescope collapsed back at the beginning of December, and you all can find the photos and the videos, I don't really care to rewatch the videos at this point. It affected, the 100 or so people who work at the observatory, the hundreds of people who have worked at the observatory, the thousands who've observed, the students who have spent summers at Arecibo, who either continued on or astronomy or gone on into other fields, the Puerto Rican students who were hoping to go to grad school in the States and return to jobs at Arecibo because it is the scientific facility in the physical sciences on the island. So it's been really devastating to see that the telescope wasn't maintained, that it wasn't considered a priority by the NSF, and that it collapsed as a consequence of that. And it was just very heartbreaking to watch. But I guess one of the few things that really I think was very special about the Arecibo Observatory community, as we saw the cables breaking and as we anticipated the collapse, or at least the decommissioning, was that the strong community has come together to reminisce about the telescope, to support the students, to really try to figure out a plan for the future of the site, to design a new telescope, to submit a white paper to the NSF, and to really think about what's the next big, audacious structure that can be built on the site to enable next generations of science. And a lot of people would say, the telescope was obsolete, it wasn't relevant, and it's been producing world-class science for 57 years, almost 60 years. Joe Taylor got a Nobel Prize for some of the work he did on pulsars there. Arecibo had observed several hundred asteroids that year and was still, finding out new things about asteroids. People have been, there's still a good deal of science that could have been produced by the observatory. And calling it obsolete was really, someone on the astronomical photo of the day called it something about obsolete, and a whole bunch of us got rather cranky. So it's just heartbreaking that it'll be probably 5-10 years at least until anything can be rebuilt on the site. until the scientific legacy can continue. But the human history of this telescope, and I think is something that's really important, and I don't think any other telescope on Earth has quite the devotion and love and affection of a community like Arecibo does. So with that, I will be happy to take your questions.
Great.
And this is, I inadvertently ran a cat rescue for 2 years when I was working there. There were a lot of feral animals that we had dumped at the observatory because it was the end of a road. And so this little kitten is named Squeakazoid, and she lives with a professor at Georgia Tech now. She was sort of our radar mascot for a little bit.
Very cool. Hold on, let me just
But
turn
if you want a cat from Arecibo, the postdocs are still finding ways to get cats stateside.
Okay.
You think I joke?
I'm sure you don't. Well, this is great. Well, we do have a bunch of questions here, so
Let's go.
let me we'll start throwing some at you. One that I just asked, I'll ask myself here is, some of those asteroids had sort of a peanut kind of sound, and any thought as to what causes that? Are there like two asteroids that eventually sort of like just hooked up?
Yeah, there's an idea that these asteroids could be the result of a merger, and that their really slow rotation rate is a result of the angular momentum conservation involved in two asteroids sticking together. You'd have to send a spacecraft to them to find out for sure. Be like, how different is the big lobe from the small lobe?
Very cool. So Dawn actually commented, this is talking about one of your slides, talking about how it was a gorgeous view, and says, as long as you're not afraid of heights. And
yeah.
and so I guess, is there any special procedures? I'm assuming not anybody can just go up there.
Right. So to go up, there are two ways to get up to the telescope. Let's see if I can. So there are two ways to get up to the telescope. It's sort of obscured here, but these stairs go down to this catwalk, and then there's also a cable car docking station here. So to go up, you had to make sure that there were no sensitive observations happening. No one was running radar, right? You're probably not going to get fried, but you don't want to be the person who finds out.
Yeah.
And also, if you have a camera with you, you don't want to be taking photos since that could disrupt some of the sensitive observations. I mean, we could detect your cell phone on Mars, right? Like.
Wow. Cool. All right. David asks, can you please compare and contrast radar astronomy versus radio astronomy?
Okay, so the big one for the big difference is that with radar you get to create your own radio waves. You know your source. You know what your radiation is like. Whereas with radio astronomy, you can't call up your local klystron producer in the Sagittarius A and say, hey, turn on. You get what you're going to get with radio astronomy. But with radar, you have control over what sort of illumination you're bathing your objects in, and so at least you know what the source is like. So when you get the echo back, you can say, okay, if the echo looks like this and the source looks like this, then we think the object will probably be like this.
Right. So you talked earlier about you get stuck in a speed trap. Basically, you're dealing with Doppler shift. That if something is going away from you, the radio signal that comes back from you should be lower in frequency, and anything that's approaching you, that radio frequency that comes back to you, should be slightly higher in frequency. Correct?
Yeah. So if you have an object like an asteroid that's rotating, the part that rotates towards you is blue shifted, and the part that's rotating away from you is red shifted. And so let's see if I have a slightly more technical slide somewhere. So here's what kind of a spectrum looks like of an asteroid when you're first observing it before you switch to the higher resolution imaging mode. So this is actually an asteroid that has two moons. This is Moon 1 and Moon 2. So the moons move really slowly compared to the asteroid. So they show up as these really bright spikes. And then the asteroid itself is more spread out. So this would be one side of the asteroid, and then this would be the other side of the asteroid, which are moving faster than the center of the asteroid. If you're seeing the asteroid like this, pull on, you will see no change in velocity. You would just see this spike.
All right, cool. Luke, or Mr. Luke asks, what's the range? Can you look at things out in the Kuiper belt?
It would be extremely hard, but the furthest thing away that has been radared is the rings of Saturn. Cool. And the rings of Saturn look really weird in radar. Actually, I was just showing this to someone earlier today. I have it in a different presentation. This is what the rings of Saturn look like. They're really strange. There's a lot of things wrong with this picture. First of all, is where's Saturn? Saturn isn't radio reflective, it's just gas, so the radio waves don't reflect off of it, and the rings cross. Because this is sort of just an artifact of the distance velocity projection we're seeing in the rings. Eventually you get to a point where it looks like the inner ring is moving faster than the outer ring. This is what Saturn looks like in radar.
Very interesting. All right. Mike is asking a couple of questions. He says, what is was the sensitivity for a normal reflectance asteroid of cross-section versus distance? I'm not sure I understand that.
Yeah. Can you repeat that? Sorry?
Yeah, it says, what is or was the sensitivity for a normal reflectance asteroid of cross-section versus distance?
Okay. I don't think I'm quite going to answer your question the way you're asking it, but if Arecibo transmits and gets back signal from an asteroid, we're getting back 1 part in 10 to the 27 of what we transmit. So we're getting a vanishingly small fraction of the original signal that was sent out to these asteroids coming back.
All right. Let's see here.
Things you can do with 73.4 decibels of forward gain.
Yeah. Really.
Practice at home.
Do you ever see, he says that answers it, thanks. Do you ever see satellites pass through the field of view? Like low Earth orbit satellites?
No, the beam is 1 arc minute. So if I'm holding my finger out on the sky, please correct me if I do this wrong. So 1 finger held out at arm's length is about 2 degrees. And so half of a finger is about 1 degree. And if you divide that by 60, that's 1 arc minute. So you're looking at this like vanishingly small patch of sky, not vanishingly small, a very small patch of sky. And I don't think anyone has accidentally gotten a satellite, but there were 2 famous spacecraft rescues done from Arecibo. SOHO was one in particular. The gyroscope had failed, and so it rebooted to use that gyroscope and spun out of control. And no one knew if it had enough fuel left on board to be worth trying to contact. And so Arecibo is a lot cheaper to use than the Deep Space Network because it doesn't have to talk to a bunch of spacecraft. So the scheduling flexibility is a lot easier. So they're actually able to communicate with SOHO, find out, well, not communicate, they were actually able to find out how fast SOHO was spinning, confirm that it had fuel left on board, and then get the expensive Deep Space Network time to communicate with it to try to reboot it not to that gyroscope. And then in 2014, they rebooted the Ic3 spacecraft that had been launched in the late 1970s. And so some ham radio nerds in Germany built this transmitter, and some folks my age using software-defined radio, we weren't even born when the spacecraft was launched. Using software-defined radio, we're able to get the spacecraft to wake up and be able to get it to spin back up. So that was pretty cool.
Cool. Here's another question that I've got is, how is the antenna pointed? I mean, it seems like it's not just always looking in one spot. You're obviously you've got to be able to look. So what's the field of view that you've got available to you, and how do they move it?
All right. Okay, we can look at this image. So this dome, actually, the dome and the big antenna. I think you can see the big antenna. Okay, so you've got the dome and the big antenna in this image.
Right.
And this azimuth arm. So the dome can move out to here. The antenna can move out to here, and that's 20 degrees. So you can point 20 degrees from zenith in either direction.
Okay.
Which is, I think you guys probably have much better pointing, much wider range of pointing on your telescope there than yours.
Yeah, we still hit trees as we get to the horizon, but that's not a problem for you.
There's chainsaws for that.
Yeah. Very cool. Well, I think at this point I don't see any other questions here. I don't know if there's anything else I was gonna.
There's another question that I wanted to answer more of. Anyway.
So. Anyway, this was just outstanding, and I really hope that maybe with the new incoming administration there'll be a little more focus on science, and NSF can find 100 million or whatever it takes to.
100 million. I think you're probably looking in the neighborhood of 300, 350 to be. I think that would be a low ball
right.
At this point.
Well. But again, I think evidenced by the asteroid that the meteorite that came in at Chelyabinsk, it's clear that these things can have a significant effect on us, and so knowing where they are, where they're headed, to make us aware of that. Again, I think one of the things I remember being up here. During when that meteor did arrive, and it's extraordinarily lucky that nobody actually got seriously hurt from that.
I know, it was incredible. I mean, I think the worst thing that happened was that some people got hit by flying shards of glass.
Yep.
And then some people got very cold because it was extremely cold out there. It was February. It's not a warm part of the world, and so having a bunch of broken glass windows probably. Right,
because they were seeing the light, and they said, "What is that light?" They go over to the window to see what's going on, and then, as you said, the shock wave finally hits and takes all the glass out.
You can go on YouTube and watch compilation videos, folks reacting to the shock wave.
Yep.
Some are. Yeah, some people do better than others.
Right, but anyway, so it was quite the spectacular. And also there was another asteroid, I guess, that came in like 12 hours later.
Yeah, they're completely unrelated. Someone I know was testifying in Congress that we've solved the asteroid problem, and then 5 minutes rolls through.
Never mind. So, all right, well. A bunch of thanks here in the chat. So thank you so much. I really do appreciate your time. This was great.
All have been wonderful.
Well, thank you.
Now Linda French owes me a favor.
Yeah, exactly. She does. Exactly. And I'll tell her you said hi, and that you're starting your list. So, all right. Well, thanks again. For those of you that may have. Tuned in a little bit later. We've got another 5 or 6 weeks of other FNLs coming down the pike. So go to our website, www.copernic.org. Also, make sure you subscribe if you're not a subscriber already. And if you like what we do here, again, bringing these kinds of experts to share their knowledge with you. If you can support us in any way through the link down below, that'll be great. So thanks again. Have a safe weekend. Make sure you wear your mask, and we'll see you next week. Take care.